All right. I think now we are at 1 p.m. First of all, I'm going to do a quick introduction. Hello, everybody. Welcome to our C.R.E.A.T.E UTC webinar series. My name is Shijun Jeff Shi. I'm the Technology Transfer Officer for the C.R.E.A.T.E Center. I'm also an assistant professor at Texas State University. Today, we are very pleased to have Steve Nolan from Florida Department of Transportation and Mohammed Amin Medesolity from University of Miami to give us a talk on shoreline protection with SEAHIVE technology. Steve Nolan has been a professional engineer in Florida since 2001. He received his engineering degree from the University of New South Wales in Sydney, Australia in 1989, and he then worked as construction engineer for a heavy civil contractor before coming to the United States in 1996. After that, Steve joined the Florida Department of Transportation. He currently leads the implementation of novel structural materials for bridge applications within the Florida Department of Transportation State Structures Design Office. Our co-speaker is Mohammed Amin Medesolity. Amin is a PhD student of structural civil engineering under supervision of Dr. Tony Nani at the University of Miami. His areas of study are focused on investigating the compressive behavior of fiber-reinforced polymer bars and exploring structural performance of SEAHIVE reinforced with FRP bars. So for today's webinar, Steve will first do a live presentation, then I will play a pre-recorded video by Amin. For the presentation, we will have 15 minutes Q&A, and the speakers are here to answer any questions. So without further ado, I'm going to let Steve share the screen and give the presentation. Thank you, Steve.
Thank you, Shijun. Okay, welcome everybody. Let me get this show on the road here. Let me know when we've got full screen. How's that look, Shijun?
Yeah, we can see it. Thank you.
All right, thank you. So we're going to talk about shoreline protection and some foundation protection as well as it relates specifically to the C.R.E.A.T.E UTC project that's going on at Texas State. So as I was introduced, I work at Florida Department of Transportation. We have an innovative materials structures section or initiative actually that I've been leading for about the last 6 or 7 years. And so within that, we look at specific materials, FRP, UHPC. We're also looking at different structural forms. And so this is where the SEAHIVE unit comes into something that I looked at originally, and then we passed it on to the University of Miami to develop, and now we're bringing in Texas State to look at some expanded applications. So I hope you enjoy the presentation today, and a lot of it is background and motivation and generating thoughts and ideas about how to best combine technologies and structural morphology. So hopefully you'll get something good out of it. I can get my slides to advance. So we'll start after I'm completed with a pre-recorded video. You've heard my bio, but this is really the real Steve. So I was born during construction of the Sydney Opera House. Worked for 3 years on some heavy civil sites and met my wife overseas and decided to move to the US shortly after that. So I've been here permanently since 1996. We're going to look at some of the background and motivation for this work that we've engaged in, a brief history of storm damage on the Florida East Coast. I know Texas has a significant history in the past down Galveston area. Maybe in the future we'll delve into that one a little bit too. We'll highlight some of the studies that were initially conducted along State Road A1A highway to look at options for protection, and then focus in on the original preferred solution at the time, and then some follow-up projects that have occurred after recent storm damage has occurred. Then we'll dig into some of the exciting developments that we're investigating, and we'll finish off with just touching on the initial scour investigation that's being conducted right now in Texas, and hopefully we'll have a follow-up presentation on that by the folks there later on in the year or early next year. And then at the end, we'll dig into some of the more specific structural investigations that's been conducted at the University of Miami that Armin's in charge of leading. And hopefully we'll have plenty of time for questions at the end. But it's always good to ask why. Why are we doing any of this? And it's pretty obvious that the costs of these extreme event and moderate events is increasing. That's a factor of increased density of development, increased density of development along the coast, and then increased severity or frequency or both of storms and other weather-related conditions. And typically you get cyclic peaks and lows. Tends to be, it seems like, an 8 to 10 year cycles, or seem to be in the middle of another one here. But if you look at the last 25 years, the cost has just grown significantly for the damage that's incurred as a result of some of these storms or floods or tropical cyclones. And as you'll see, a lot of it is related to water damage, whether that's from wave action, stream flow, or other related hydraulic events. This map from 2020 shows the locations of all the different kinds of hazard disasters that have occurred. Should be pretty obvious what's most significant in what region of the country. In Florida, we're susceptible to hurricanes mostly, at least at this point. So if we look nationally in the US at bridge failures or causes of bridge failures, at least half, and sometimes some studies quite a bit more, are hydraulic related. And so that's typically the result of scour or undermining of the foundations. Looking a little more broadly, this study or survey by Zhang et al. Looked at both the US and China and found similar trends there with the hydraulic events creating the majority of the damage to existing infrastructure and bridges more specifically. So this was something just from a week and a half ago that caught my attention. When we look specifically at the coast or coastal infrastructure, highways in the case of A1A that we're going to be talking about today, the natural protection is typically the sand dunes, which are quite often removed during urban development for improvement of views or whatever. And so as we've grown to appreciate the advantages of these natural defenses, we've invested significant resources in rebuilding or renourishing the beaches and sand dunes periodically after a storm event. But it's always, it seems, a never-ending battle in that the sand never returns in full back to the shoreline during the calmer periods, and so we're continually at risk of more and more damage. And that could be a function of a number of factors, whether that's increased severity of storm activity, whether that's a rising mean sea level. All these things sort of play a bit of a part into that. And policy decisions too play into that for development along the coast, and insurance and reinsurance incentives. So it's a very complicated issue as to what the cause and potentially what the solution is. As engineers, we're tasked with trying to provide safe and efficient and effective infrastructure for the community, and so that's what we're focusing on here. Whether you're supportive of protective measures along the coastline or not, that's obviously can be controversial in some communities. But if we look at the northeast counties of Florida, St. John's, Flagler, and Volusia, they've been subjected to quite a few storms in the last 20-25 years that's resulted in significant damage, and we seem to be replacing or repairing the highway every decade or so due to a major event. So most recently with Hurricane Nicole, even it's not just the highways now that are at risk, and so some of these large condominium complexes that are adjacent to the coast starting to be undermined. You can see the piles hanging out at the bottom of that significant structure there. So it seems like we're going to need some solutions to both balance the needs of the community for access and use of the natural resource of the beach, plus protection of infrastructure until we decide whether to retreat or some other activity. But we started looking at different protective measures back in 2016 and developed this what we call a design standard development report in the department. It's just the initial seed idea phase and gathering information. There's quite a lot of attempts and different products out in the world that have been used over the years, and some of those work very well. Most of them are all proprietary and restrictive in their use, and didn't seem any of them really fit the need of what we needed as far as scale protection for bridge abutments, retaining walls, and potentially intermediate piers and piles. So we sort of settled on this shape of the hexagon just because of the structural efficiency of it and the adaptability, like an interlock. We looked at the potential for it being a substitute long term for rubble riprap. That's the go-to method of shoreline protection. The challenge in Florida is that we don't have heavy density rock. We have a lot of lime rock, which can be pretty robust, but it doesn't have the weight that sometimes is required with these large energy installations near the coastline. And so we're importing granite from Nova Scotia and maybe from Georgia. And so that's not an insignificant cost. And so we're looking at some sort of modular system potentially that could replace that, be a little more efficient, both environmentally and structurally, and adaptable in the future. And so here's an example of where we would normally have a rubble riprap abutment and potential use of different hex-shaped modular structures to protect that. So here's just a little scale mock-up that I built back in 2018, and just as a concept, just to see how the water flowed around it. Nothing very scientific about it, but it was just a fun project just to see if this was something that was really worthwhile and practical. We had worked with University of Miami on a project looking at very durable materials, FRP specifically. And so as part of that project, follow-up to that project, we looked at some other adaptions that could be utilized in the future. And then most recently, we started to look at the scour of bridge piles and bridge piers, and looking at trying to develop something that might be capable of retrofitting an existing bridge to mitigate scour. So we're very early in that development phase, but you'll see as we get through this presentation a little bit more of what's been done to date. So focusing in on Flagler County, after some significant storm damage, we invested money in hardening the right-of-way of the coastal highway. We didn't touch the beach and toe of the sand dunes, although they had been removed from the hurricane. This was motivated by Hurricane Matthew in 2016. As you will see, we've been looking at it for quite a while. It seemed to be a continual problem. Flagler County did not have a recurring contract with the Army Corps of Engineers for renourishment of their beaches, so that could have been part of the problem. But there's always a concern with any system of disrupting the national environment, so there's always concerns about what the effect this will have on sea turtle nesting and other habitat. So there was a 1 mile section we will call segment 3 that was the most vulnerable to scour and had the most damage in the past. And so that's the section that initially focused on. There is a section to the south, segment 2, majority of which is, it had a federal renourishment project planned, and there was a lot of technical issues with getting rights of way to do that work. And so it's been held up. I think it's just about to start. It's sort of been like 5 years, and that sort of is indicative of some of the challenges if you're going to rely on a renourishment program. You need to have all the agreements in place to be able to do that and reliably come back after a severe event to maintain protection. So going back to the beginning of this century, I guess it would be, we had a pretty severe storm season in 2004, 2005. 2004 was worse for Florida than 2005. That was Katrina. But during that period, there was significant erosion along the coast and damage to the Highway A1A. So it seems, I don't know if you can hear that background noise, but I hope it doesn't bother you too much. I have a landscaper outside right now. We looked at 6 different options for protecting the shoulder of the highway there, just behind the sand dunes. All of them pretty much traditional retaining wall systems. The single pile wall was really the last one that the building industry is very familiar with, but we hadn't used it a lot in civil infrastructure construction. And so that particular system they looked at then had a steel H pile in the middle for reinforcement, which ended up not being the reinforcing option that we chose. Because of the severity of the storm season in 2005, there was a emergency contract, so they went and built a short section of steel sheet pile wall with concrete cap tied back. You can see there in the top right. This was I presume intended to be a somewhat temporary solution, 20, 25 years. I don't really know the full details and the motivation, but it provided a great opportunity for us to go back and look at the durability of sheet piles in this type of environment, to see if it was viable to design these systems with, sacrificial thickness. It was quite surprising, though, the amount of deterioration that we saw in the first 7 years. Partially, I believe, because of the abrasion of the sand, just accelerates the corrosion beyond just the concerns with the constant wetting and drying in the chloride environment. And so we have corrosion rates established for aggressive environments, but they're not really anticipating this type of application. And what we found was the corrosion rates locally were up to, well, more than twice what the worst case we predicted in the past. So the microenvironment is very critical to the use of some of those guidance that's out there in our structures manual and other engineering documents. So moving ahead 10 years, Hurricane Matthew came through. That was the next biggest storm, and it did a lot of damage along the coast. As you can see there, some pretty impressive erosion of the highway, significant disruption to the community. This is the main access route along that section of the coast for businesses and evacuation. So it was a concern to the state of Florida that this seemed to be occurring more frequently. And if you look back at that steel sheet pile wall that we talked about earlier, you can see there that it's totally exposed at the end, and essentially that had to be removed. So the project that was designed was a second pile wall for segment. It says segment 1, but I think it's actually segment 3. And segment 2 was unprotected, which was a little bit to the south. And so we had like a 1 mile second pile wall that was eventually buried by sand dune and revegetated, which we presented in the 2019 Florida Shore and Beach Protection Association conference, tech conference in St. Augustine. So there's quite a few details on that available there. The project was finished in, I think, July. And then in September, we had Hurricane Dorian come through and erode most of the sand that we had placed or replaced after completion of the project, probably 75%. There was another storm, 2020, not as significant, and then 22 we had Hurricane Ian that really did some damage along that coast, but the second pile wall stood up well. There was no, you can see all the vegetated sand dunes on top remained in place, and no damage to the highway. The section south of that wasn't hardened with the second pile wall had significant damage again. Looks very familiar to the previous scenarios, and so the state was charged with expanding that protection that we currently provided. Here's some more photos. Hurricane Nicole, that was a month later. It didn't necessarily scour any more sand away from the base of the wall by the end of the storm, but it did damage areas to the north even more significantly, where there was no protection. So the wall did its job and allowed the county to go back and replenish with sand once they got the permits. But as I said, that takes quite a while, and it's not going to happen probably for another couple of years. When we go back, all this rubble that you see at the toe of the wall there, that wasn't part of the the last project that was previous attempts to protect the highway. And so that sort of obstructs the what remaining beach there is. And so as part of the designs we don't use rubble as a tow protection scour, just because of the residual concerns. So looking at these projects for this year and next year, is about a mile to the south of the first project, which we call project number 3. Project 2 was the Army Corps of Engineers. And so this is completed design, is about to start construction. And then there's a section to the south of the county line there in Volusia County. It's about twice the length of coast, 2 specific areas with a similar system, and we'll look at some of the details. They both use sinker pile walls. This is the original technology that came from the building industry that was utilized effectively in the first project. There's plenty of information out there that you can access. So this is a concept we're looking at for improving the efficiency and the economy of the sinker pile wall by incorporating precast casings in the hexagon form, and potentially supplementing that with units at the toe to reduce the amount of scour or recharge the sand as the storm encroaches on the wall. Originally, these projects were envisioned with steel rebar, but as the department moved towards the use of FRP, we were able to incorporate glass rebar, GFRP rebar for short, into those projects. There are significant advantages of both listed on the screen there, but the main motivation really is durability and to eliminate corrosion. There are limitations also with both steel and GFRP, and so being able to work with those limitations is part of what we do. The costs are more, let's say, for FRP than they are for plain carbon steel. Those cost differentials tend to reduce as you get to more expensive alloys that are more corrosion resistant and significantly less than stainless steel, which would be similar in its durability performance. But what we are finding is that as you get to larger and larger bars, the cost differential tends to go away, and so we're also looking at this for other applications. Steel rebar has a long history of development. This is just something I copied out from FHWA publication. So FRP rebar it's not 100 years behind, but it's about 80. The ASTM publications that have been formally adopted in the US, there has been specifications in other countries published a decade probably before this or two. Really only got approval in 2015 under ASTM, 2017 rather, under ASTM, and there was an update last year to a higher modulus specification, which adds some advantages to us to improve the economy of these structural systems. So back when we were looking at the first project, those were the costs of the steel rebar versus the GFRP. With today's market limitations, the cost of steel rebar has increased significantly. It fluctuates quite a lot, though, depending on this is an in-place cost from the contractor. That's always a moving target. But the important thing that did happen between the first project and this next project was the release of a high modulus, high strength specification. So we're able to reduce the volume of GFRP rebar. This is a lot on this slide, but basically it's just a comparison of a traditional steel reinforcing design with a GFRP one. And you can see that the area of reinforcing 14 square inches to almost 20, there's a significant increased area required, and that's mostly due to the stiffness, not the strength of the reinforcing. So we have limitations on the deflection that these wall systems can have to avoid damage to the highway shoulder. So as the FRP rebar properties improve, stiffness and strength, then that's really going to help drive down the costs. So if we look at this, the next project, the one at the southern end of Flagler County, the designer has a slightly taller wall there, and so the actual design ended up being 28 square inches, which was a little bit more due to deflection. And so as we started looking at the project and the next project that accompanies this to the south, and with the release of the ASTM with high modulus, high strength rebar, we encourage the design build team to consider using the newer specification, which was not necessarily in their original contract. And so they've taken a look at that. And you'll see in the third project that they're actually reducing the volume or cross-sectional area of reinforcing required in the seeker pile. And other differences between the first and the second and third projects is the tapered toe was found to be unnecessary and expensive, and so we've eliminated that. There is an increase in the area of stirrups. So again, that's related to some of the changes in the design specifications. But as we look at the last project, which really is Volusia County, it's not really Flagler Beach anymore. That one, we're able to go back down from 28 square inches to 20 square inches using the grade 3 high modulus reinforcing. So that's a pretty significant 30% reduction thereabouts in reinforcing. So as we improve these standards and the manufacturers and show us what they can do, we are able to take advantage of that. So the project now is design's complete. Tomorrow is pretty much the final comment on the final plans and construction on the southern Flagler Beach section will begin. So if we look at the existing design and then the new design, and then potentially enhancements using other precast accelerated construction methods, we're looking at adaptations of SEAHIVE to this system, and depending on the structural demand as the wall height potentially gets higher, there is ways to reconfigure these hex shapes into two-dimensional walls to improve the structural efficiency. So like a sign wall, that actually is a specific wall type that is available, but that's the beauty of these hexagonal shapes. You can do a lot of different reconfigurations. So looking back at some work that was done specifically for a scour investigation. It was really wave attenuation, is what we were looking at in this project. So that's an C.R.E.A.T.E idea project number 213. It was led by the University of Miami. And so they did some wave tank testing to look at the wave attenuation possibilities with different configurations, different amounts of perforation. And then most recently with the C.R.E.A.T.E UTC, we're looking at potential applications for the scour mitigation of bridge foundations. So this is some initial work that's been done at Texas State, looking at a single pile in the flume. So what's not surprising, but what they found was there really wasn't that much benefit in this single configuration when you compare it to a circular pile. In fact, it actually scoured a little bit quicker, whether that's because of the jetting effect of the holes. Really needs a little bit more investigation to be done. There is some computational fluid dynamic modeling work that's also being done parallel to this to look at trying to optimize the system, but the real test will be when you start looking at multiple systems. So that's it for my section. We're going to go ahead with Eamon's section here and looking at some structural testing at University of Miami. So thank you.
Hello everyone. First of all, I want to thank you, Steve, for presenting this first part of the presentation. And before starting my presentation, I want to express my appreciation for providing me with this opportunity to present my work in this webinar. My name is Mohammad Amin Mizar Sultani, and I am currently PhD student at the University of Miami. Today, I want to present my work on the structural performance of the SEAHIVEs under the compressive and flexural load. In the first slide, I want to introduce my test setup for applying the compressive load on element. We applied the compressive load statically and cyclic loads on the elements. For measuring the strain gauge strain at the different locations, we use 8 different strain gauges, and moreover, we use 2 LVDTs at the both ends of the elements to capture the displacement when we apply the compressive load on the elements. As you can see in this slide, we used 2 steel plates on the top and bottom of the elements to apply the uniform compressive load on the SEAHIVE elements, and we used 2 hydraulic jacks for applying the load. This is the result of the statical compressive loads on the SEAHIVE elements. As you can see, maximum load reached about 31 kip, and the displacement at the maximum load is about 0.43 inches, and the cracks started to initiate in the load of 16 kip. This is the result of strain gauges. As you can see from the result of the strain gauges, the method of applying the load applying the compressive load on the element is uniform and acceptable, because the pattern of the strain gauges for those that are parallel together in the cross section, the pattern of the strain gauges are almost identical. Apart from the statical compressive load, we did some cyclic compressive loads on SEAHIVE elements. The result was almost the same. The maximum load reached about 40 kip, and the displacement at the maximum load was about 0.75 inches. Moreover, load at the cracks started to initiate at the load of 15 kip. Apart from the compressive loads, we did some flexural load again with static flexural load and cyclic load on the SEAHIVE elements. We used two hydraulic jacks for applying the flexural loads on the elements, and we used steel knives on the top and bottom of the elements. For capturing the displacement, we used two LVDTs in the middle of the elements on each side, and for the strain gauges at the different location, we used two strain gauges on the top of the elements and two strain gauges on the bottom of the elements to capture the maximum compressive strain and tensile strain when we applied the flexural load. This slide shows the pattern of the failure after applying the flexural load, statical flexural load, and the results show that cracks started to initiate at 70 kip, and moreover the ultimate load was about 60 kip when we applied the flexural load on the elements. It should be noted that both loads represent the total load of the two jacks when we applied the load. This slide shows the implementation of the elements on the Miami Beach and the spacing between the elements and units. And these are some pictures we implemented we used these units in Miami Beach in March 2023. This is an interesting photo. It shows that these elements provide a safe habitat for the marine creature, and marine creature. It shows that marine creature lives in a harmony with our new elements. These are interesting videos. I want to show these videos to all. On the left side, there are some 3D printed stuff, and the right side shows the Fort Walton design, which we use such elements in the real world. Fabrication of going to extract.
Sorry, there was some dead space in the middle of that.
And it is the future investigation on the SEAHIVE. We are going to extract some course for conducting quality control and quality assurance on the fabrication of the elements. We are going to extracting course on SEAHIVE. Providing the compressive strength of the concrete used for the fabrication of the SEAHIVEs, and moreover performing ultrasonic pulse velocity on the extracted cores. In addition, we are going to measure the density of the concrete cores and evaluating the bulk resistivity on the extracted cores. Apart from mentioned procedure, we are going to conduct some additional flexural tests, especially the cyclic flexural tests on the SEAHIVEs, and providing FEM, a finite element model for our tested SEAHIVEs. Moreover, this slide shows that other future research on mentioned elements. We are going to use such elements as a scour counter measures for the breach piers. And I think it was the last slide, and thank you very much for your attention.
Okay, so that's all we've got. So I think now we can go to questions if you want to take over, Shinjin.
Hey, Steve. Yeah, I actually need to go to a class. So Stacy, she's going to lead the Q&A session. So Stacy,
Okay.
I also have to go to class, but I guess yours is more important, is what you're saying. So we don't have any questions in the open forum yet, but if you have any, feel free to type them in the Q&A or in the chat. I guess I'll ask my own self-serving question, because you know, while showing the Flume video, said that it wasn't surprising that there was more scour around the SEAHIVE as a standalone element. So what would you say is the optimum configuration to minimize scour? What should we use? What should we test next?
So when I was studying that video, and sometime we need to get together and talk about whether the bottom holes were sealed or not around the measuring stick. But it looked like there was a jetting effect with the holes on the back side, or either coming through from above and down the bottom. So that's not something you necessarily anticipate. And so we talked about, well, maybe when there's a larger volume of them, then that localized jetting effect might not occur. We've talked about horizontal applications. I know that's something you're curious about. The ability of them as a circumferential structure, let's just say, rather than the pile themselves, I think is probably more potentially viable and useful from a retrofit perspective, because
Sure.
you're not going to be able to go in and well, you don't want to go in and replace a pile if you have to. And so but certainly if it helps in the original pile condition, then sure. But that wasn't necessarily envisioned as being the best application.
Sure.
But it's good to know, yeah, up front what you don't know, right? We never know what we know until we start digging into it.
Sure.
Not sure I
yeah.
answered your question, but
I mean, we're on the same page. I know what you're talking about, and I could answer that, but we could have our own side conversation. But here, so the 3D printed part was quite interesting, and its application. What was the material that was used? Is there any printed test that's been conducted related to the novel specimens?
So I'd probably have to defer to Landolf to answer that in more detail, although I do have some knowledge of the system. I don't think they've done a physical test yet. One of the things that we're trying to figure out is we don't even know what the design load should be for this type of, depending on the application. So yeah, we can test it in shear or flexure, but what does it really need to have? And so to be able to tune these systems to be the most economical is going to be a challenge. But that 3D printed HAD system was quite adaptable in that it had voids that they were able to place GFRP dowels or bars inside and then post grout it. And so there's a lot of flexibility on the number of units that could be used. The advantage, to me, the advantage of the 3D, or the cluster units, I like to call them, is that is for the base, because when you're doing a horizontal application, there's a concern that the whole stack will collapse as the bottom unit spread. And so the advantage of having a pre-monolithic cluster unit for the base is that you end up with a foundation that can't spread, and you're not relying on connecting the elements, especially below water. So and you can scale up the size of them, I guess, to reduce the amount of shipping, but we're not really sure if the economy in 3D printing is really going to be let's say, a panacea for this. I think there's room for both, or several different construction technologies, and the material is quite interesting of what can be used, because not only structurally but biologically you can get into designing a mix that's a little more friendly to whatever particular organism you're trying to attract, reduce the alkalinity or some other feature. And so in that respect, LC3 concrete seems to be quite, let's say, not preferred but attractive in attracting different marine creatures. So we'll see where that goes.
Cool. Well, just so Landolph answered that the material's from Titan and that they're doing the testing right now. He doesn't get to speak because he's a participant.
Okay.
As a follow-up, I think, to that question, someone else asked, do you have any comparison in total cost, including construction cost of the SEAHIVE unit and it says steel reinforced piles, or I guess your auger cast pile example maybe?
Short answer, no. Long answer, we're working on it. It depends. We're looking at the hex pile without voids and things, so not really a SEAHIVE per se, but just a structural element. And we think there's potentially some efficiencies there that we can utilize in combined construction. We already have cylinder piles, let's call them, for bridge construction, but those are, again, I know they were proprietary. I think the patent's expired, but those are only really manufactured by one producer. And so what we're looking at is something that's universally applicable. And we're trying to utilize systems that, shapes and dimensions that are able to utilize existing form systems, just with inserts, which is not always the most economical long term, but until we scale up or identify the advantage to scale up, then we're going to have to be constrained a little bit on how much we ask the precasters to invest in their forming systems. So, but there is challenges with hollow piles that we have seen with water hammer and some other unique things that have resulted from degradation of the liner materials. And so we continue to try and resolve some of those challenges. But the large holes that are in the side of the SEAHIVE unit would eliminate a lot of those issues that we have. They just eat into your structural capacity a little bit, but it's all right. We can calculate that.
Okay. So since y'all are working on this, does FDOT have a resilience plan or spec for managing transportation assets, including foundations, pavements, and bridges?
We do. We have a whole program on resiliency. We have a resilience action plan that's out there on the website. You can look at that. There's a dozen or so projects in each district that are identified. There isn't, well, there's a couple of shoreline coast, I forget what they call them, coastline mitigation projects, 5 of which I know are on the Keys corridor. But we're sort of very early in the stages of identifying the most critical projects that need to be funded. And so typically our bridges are pretty robust. If you remember the hurricane last year with the scouring out of Sanibel Island and the claims in the media that the bridge collapsed. Well, actually it didn't. The bridge stood up fine. It was the approach spans that collapsed. But all those approach seawalls and things were damaged, and so we learn a lot from that event, and so we continue to improve. Job security, right?
Cool. All right, someone else wants to know, have you noticed any performance issues with SEAHIVEs as a result of clogging?
Clogging?
Yeah.
No, I mean, I imagine, well, depends obviously on the application, but if you're looking at, say, in a vertical orientation as a bridge pier or a protection around a bridge pier, there is potential that you could capture logs and branches and things that are flowing down during a flood. And so that's always a concern, debris. And clogging as far as filling with sand and mud, I mean, that's what we want, because the shape sort of delays the erosion that you can have, and on the beach it allows the sand to be washed out at a slower rate. And so it has the cloggingness of it has its benefits too.
Cool. I got to clarify that they're testing and designing, considering both solid and perforated, to have an upper and lower bound in terms of the porosity, I guess, considering clogging.
Yeah, the larger the porosity, the more wave dissipation you get, the less reflection you get, and vice versa. And I imagine the same will be true in the riverine application as well. So
cool.
Be speculating beyond that.
All right. Well, since you mentioned the dissipation, what amount of wave energy dissipation can the SEAHIVE produce?
If you go to the NCHRP Idea Project 213, it actually has some tables and values in there, but I think from memory, if Landoff can help me here, I think it was about 40% dissipation.
Okay. Depends on the
Depends on,
configuration.
again,
Ooh,
depends
75
on
to 85.
Oh, 70 dissipation. Okay.
Ah,
It depends on the number of units in the horizontal application. They did a bunch of different studies looking at combinations of SEAHIVEs and other quite articulated looking structures, and it's the height that's more critical. I think they found the length has a little effect, but not nearly as much as what the height does. The challenge with the height is that during a storm surge event, you don't know whether it's high tide, low tide, how much surge you're getting it, and so you've got to have a system or a series of systems that's adaptable to different levels of flooding. And so that's something we're working on, trying to evaluate the best way to manage that.
that's cool. Well, we're rounding out our 1 hour webinar. We have 2 minutes left-ish. We had some good questions from the group, not as many crammed from me, so that's always nice. Any last burning questions for Steve or Landoff, who's answering in the chat?
You can always email. You can follow
Yeah,
up later.
emails are up. And then all of our webinars are posted, so you'll be immortalized forever, Steve, on the internet. So you can go back and watch it again or get his email that way. But if there's no more questions, I would say that got a nice talk. Thank you for coming. Yeah, so we really appreciate you coming and speaking to us today, Steve, and for all the information and being willing to answer all of our questions. The next C.R.E.A.T.E webinar we're going for like every other month-ish will be in early June. So in early June, we'll have someone talking about pavement erosion and reinforcement with inspired mangrove systems. So that'll be a little bit more of a geotechnical talk for our next webinar. We're trying to be diverse in our topics as well. So be looking for that announcement. We'll put it on LinkedIn and share it broadly. And thank you again for your time and for the questions, and hope to see you in June.
All right. Thank you.
Thanks, Steve. That was a good talk. We appreciate it.
You're welcome. yeah, I I kept adding to it and adding to it. I was afraid I wasn't going to get done in time, but it's right on schedule.
No, yeah, you were. That's why I told Jeff. I was like, oh, there's 56 slides, but no, you kind of worked your way in and then went through. So we'll trim out the discussion at the end, and then we'll post this so that other people can go and look at it. We have the SEAHIVE. That was like just our first trial, just even figuring out if we could make one, like literally, because we were just like, what can we find in the lab that's like kind of similar? So he just has it with a replicate to compare to the to a monopile. But I think the next thing we're gonna have him do is have the holes in the sand. Would be interesting for one, and then because that was actually filled in. Yeah, but those are too big for our flume, so we can only have 2.8 centimeters.
I've been making them out of toilet roll holders and paper towel.
That will not work in my flume. But Landau says he has some extra ones that he's going to send us maybe, or we're going to try to mimic it. But I'm more interested. Like, I talked to the TechStop guys, and they were more, well, if it's scour, we're going to go back and we're going to retrofit. So kind of like, how small can we make it basically, and go and dump it in the water and it'd be helpful. So that's what we're going to move on to next.
Yeah, so that's what I was trying to look at, what our typical pile size was and how, you know, you could get a group of them around it if you were doing the vertical application.
I was thinking like a skirt, right? Because if you drove it a little bit, you densify the soil anyway. And then if you're already mitigating wave energy, then that further would help it around it, in my mind.
Yeah, and if, you know, and as it does scour out, it could settle, you know, and follow the scour hole and still potentially still mitigate.
Yeah.
And then you just have to stick another one on if it goes far enough.
That's what I told Rudy, the student that ran the test. I was like, well, if it makes more erosion, but it doesn't erode around the foundation, who cares? It was sacrificial. Yeah. So pick it up, try again. But cool. But as we, like I said, we're just now getting going. So it took us a while to get our flume up and running. And then they had to use it for teaching a couple of weeks. But since summer's about to start, we're about to go start running through those. So it should be pretty fun.
All right. Sounds good.
We'll give you an update, but I'm sure I'll talk to you soon.
Okay. Sounds good.
Thanks again for your time. Bye.